What's up, guys? Welcome to the 12 ISLs of Christmas. To start it off, we're going to be solving Shortlist 2021 problem N1. And we're starting off with an easy problem, and we'll gradually get harder until the end of the series. So anyways, the problem is find all positive integers n greater than or equal to 1 such that there exists a pair a comma b of positive integers such that a squared plus b plus 3 is not divisible by the cube of any prime, and n equals this expression shown on screen. So the thing that stands out the most to us is this condition here, because we want to somehow use that. But also we want this here to be an integer, because that's definitely an important fact that we need to use. So one thing we can do with these type of fractions, if we want to show that they are integers, or if we want it to be an integer, is just keep subtracting integers from it, because an integer minus another integer is always an integer. So let's see what we can do. Well, we have two of the terms have a b, and the other one is just a constant factor. So we can get rid of that b so that we can only make it dependent on a in the top, and that would be really good. So let's go ahead and try that out. So we have ab plus 3b plus 8 is, if we factor out the b, a plus 3 times b plus 8. And we need to subtract some constant k from this. So n minus k is equal to all over a squared plus b plus 3, then ab plus 3b plus 8, minus, then we have some factor k times a squared plus b plus 3. And the coefficient of b in this one is negative k. And we would like that negative k to cancel out with the a plus 3. So might as well make k equals a plus 3. Then we have a plus 3, then a squared plus b plus 3. So this is what n minus k is if we let k equals a plus 3. Then this is an integer. And if we expand out the top, we end up getting, we get negative a cubed minus 3a squared minus 3a minus 1 over a squared plus b plus 3. But the numerator should be immediately trigger, because that is just negative a plus 1 cubed over a squared plus b plus 3. And this means that the quantity a plus 1 cubed over a squared plus b plus 3 is an integer. And since it's obviously positive, it must be a natural number. Alright, so now we know that this quantity here is a natural number. At this point, we're kind of stuck, because this denominator can be anything. It could be any divisor of a plus 1 cubed, and that could give infinitely many values of n, which we would not like to be the case. However, this is where the problem condition comes in. A squared plus b plus 3 is not divisible by the cube of any prime. So that means that cases where a squared plus b plus 3 is a plus 1 cubed cannot work, because a plus 1 is greater than or equal to 2, and any prime dividing a plus 1 will have an exponent of at least 3 in this right-hand side, which means it has an exponent of at least 3 in this left-hand side, and that's bad by the problem condition. So let's see what exactly is going on here. So suppose that we have a prime power p to the k dividing a squared plus b plus 3. Since we're dealing with the cube of any prime, it makes sense to let a prime power divide this, so that we know that k is equal to 1 or 2. Because if it is 3, then it violates the problem condition. Then since this quantity here is an integer, we must have p to the k also divides a plus 1 cubed. And this means that p divides a plus 1. because that's the only way we can have p to the k dividing a plus 1 cubed. And then whenever we square this, we end up getting p squared divides a plus 1 squared, or p cubed divides a plus 1 cubed. So if we look at this last one here, then we notice it's kind of strong because this k is at either 1 or 2, and we have an exponent of 3 here. So obviously that's going to be true. But if we look at this one here, we note that if p to the k divides this, then p squared divides this. And that means that this is also p to the k because k is also less than or equal to 2. So therefore, if p to the k divides a squared plus b plus 3, then that means that p to the k divides a plus 1 squared. And this automatically implies that a plus 1 squared over a squared plus b plus 3 is a natural number. And this is really nice because this term here is degree 3 while this one is degree 2, which, as I said earlier, gives for a lot of options. However, this one here has an exponent of 2 on top, so each side is degree 2, the numerator and denominator. And that makes it for very limited options. Okay, so now let's actually finish this off. If we expand a plus 1 squared, then we get a squared plus 2a plus 1 over a squared plus b plus 3 is a natural number. And we can get rid of the a squared term because that's what dominates the numerator. So if we subtract 1 from this, then we get this minus a squared plus b plus 3 all over a squared plus b plus 3 is an integer greater than or equal to 0. And if we expand this out and simplify it, we get 2a minus b minus 2 over a squared plus b plus 3 is integer greater than or equal to 0. So what happens if it's greater than or equal to 1? Then we have 2a minus b minus 2 is greater than or equal to a squared plus b plus 3 because it's greater than or equal to 1. And when we rearrange this, we get 2b plus a squared plus or minus 2a plus 5 is less than or equal to 0. But we can write this as 2b plus a minus 1 squared plus 4 is less than or equal to 0. All of these terms here are positive, so that's bad. So the only way this can be an integer greater than or equal to 0 is if it is equal to 0 itself. And we can get rid of this denominator here because that means that 2a minus b minus 2 is equal to 0. This means that b equals 2a minus 2. So let's plug in and see what happens. We get that the numerator of n is a times 2a minus 2 plus 3 times 2a minus 2 plus 8, which is after expanding 2a squared plus 4a plus 2. And the denominator is a squared plus 2a minus 2 plus 3, which is a squared plus 2a plus 1. Therefore, we must have n is equal to 2a squared plus 4a plus 2 over a squared plus 2a plus 1, which is equal to 2. This means that the only possible value for n is 2. And indeed, we can set a equals b equals 2, because then b equals 2a minus 2, and this gives the desired result. And we can indeed check that 2 squared plus 2 plus 3, which is 9, is not divisible by the cube of any prime. So therefore, the only possible value of n that works is n equals 2, and we have solved the problem. So the thing to take away from this problem is that we always want to divide out factors that are annoying, such as the b and times a plus 3 here. And when we get to this here, we want to try using the problem condition. Because we originally had it that is 3 there, but by using the problem condition in a very smart way, we get rid of that. And at this point, we just get rid of the dominating factors, which is a squared and a squared, and we use size. This is a very common technique in proving that a number is an integer or trying to find when it is the case. So thank you so much for watching, and I'll see you in